all about right. Okay, so we're gonna really sort of hit the middle section of this class now, which is where a lot of the, I'd say sort of the meat of the matter is. So there was a lot of review in the first part, and then we looked at things that are, while a little different than what we'd seen before with these superscalar designs, they weren't really radically dissimilar in how they were trying to get work done. They were a little wider, they were a little deeper, right? They relied on the compiler more than the hardware, but they all still basically did an instruction followed by another instruction, followed by another instruction with some forwarding, right? We're going to now look at something that runs a bit differently. And I'll do some asides here to sort of get some other perspectives from areas that didn't necessarily succeed commercially. Not all this is in the slides, but we'll get through it. Okay. So I don't think the bottom's cut off. So my apologies for this resting a little low, but should be fine. So we've covered statically scheduled in order, VLIW superscalar, and then we've mentioned that you can combine these two together with something like the Titanium that's doing static superscalar across VLIW. But my suspicion is that most of the things that you have thought of as computers that you have owned actually work this way. Right? Yes, there are lots of computers. This has a computer in it. This computer is not this. But anything that you had as in a box, whether that be a laptop-shaped box, or even, unless you were a really, really, really early adopter in smartphones, even your smartphone has been much more aggressive. Works a different way. Right? And so here what we're going to say is, if you think back to those dependence graphs, right? If you think about a fundamental problem with in-order machines, is that they have a very limited visibility into that dependence graph, right? If the compiler happened to put a run of parallel instructions back to back, great, I can exploit that. But if you think about the scale and scope of a lot of these graphs, that's not going to really be possible to get very large scale exploitation. And we have been able to find a lot more parallelism and then exploit it, depending on how far you want to dig down on your budget and in what you're looking at, to go a lot further. Okay. So I want to foreshadow, these are going to be two slides that are going to appear later in the deck, so don't worry about reading all the text. What I want you to focus on is where we're trying to go, right? So the first question is, and this is something you should always think about before you try to go and do something new, what's the potential benefit, right? So this is a measure of the amount of instructions per cycle that an idealized, i.e. completely and utterly unimplementable, right, machine could actually extract from these programs. Right? So you'll note that these numbers are quite a bit larger than the 2 to 4 that we were playing around with in our simple in-order land. Right? So there is a lot of parallelism there. So the question is not, do programs have parallelism? The question is, can we extract and exploit it? Right? There is an enormous amount of parallelism potentially possible. It varies a lot. Some things are a lot more serial than others, but even the most serial of these, again, under a unimplementable idea of a machine, a perfect machine, right, could get a lot more than 2 or 3. And again, to foreshadow, don't dwell on this. We will come back. This slide will be examined in all of its gory detail much later in the slide deck. We are going to need some different structures to go and mine that, right? So this is the sort of scale of the complexity of the design that we're going to be looking at. These are all the moving parts, right? So again, keep that in sort of your head. This is a lot more than your simple in-order pipeline, but it's not, inscrutably alien, right? Okay. So let's go back again and think about, everything starts with the dependencies the program actually has. right? So when there are write after read, write after write, read after write, the one that matters most at the end of the day is usually going to be read after write. Right? This makes sense. It's very difficult for me to do anything with a value that hasn't been computed yet. Right? The others, they're games that can be played. There's really no way to avoid sequentializing these instructions. Right? Now, we saw a technique with single static assignment where the compiler tried to avoid write after read, write after write, both to enable some static optimizations and also to even make the final program. Yes, it eventually has to map back down to a finite number of registers, but can do its best to avoid these resource conflicts. And if software could do it, then at least technically, there should be some way that hardware could do it too. Right? It's not always a good idea to try to do things in hardware that software can do. The scope, the time may not make sense, right? But at least we should understand that this is possible, right? Resources could be renamed. If everything had a unique name or where things were going and being read from, then you'd reduce down to read after write. That's going to be our goal, right? We're going to be computer architects against war, but only write after read. We still happily fund the military-industrial complex. Now, what we haven't talked about too much yet, and what will continue to be a bit of a challenge, single static assignment or something like it will help with war and waw on registers. Doesn't really play out the same way with memory. All right, so think about it from this perspective. If I want to give a new name to another register every time I write to an add instruction, fine. But, and I can make copies, there are also things I could do. But the challenge with memory is technically after any write to memory, I need a new version of all of memory, right? Because I don't know what the address is that I wrote to, right? So if I actually knew statically what all the addresses were, then it'd be just like the registers. Right? I wrote to exactly this location. I can feed through and understand my dependencies. But the way that memory is structured is somewhere at runtime, we will dynamically construct what address within memory you're going to go to and write. Somewhere later on, we will dynamically construct somewhere in memory you're going to read. And unless you give me a lot of additional information, it may be impossible to prove whether those are or are not the same location that was read and then written to. Right? Especially if your program has bugs. Oh, memory bugs. So you have a lot of maybe dependencies, right? And this is rough. Moreover, think about when you would actually know. Let's assume even you could do some renaming, right? You would not know how to do the renaming until after you'd already done most of the instruction, right? Everything but the memory access itself. You'd already have to compute the effective address. Right? So we're going to have to do something else, right? This didn't solve that in the first place, even with lots of static analysis. Hardware is not going to magically solve all of the memory dependence orderings either, but we will do our best to make the common case fast. That's about as far as we're going to go there. Okay. So control dependence, right? So again, this was basically a challenge if we were looking at our statically scheduled in-order machines. Right, so if you looked at where we were looking for parallelism, we did not really look across branches, right? Because we didn't know, well, which side we were going to execute. So, to get rid of that, you got things like predication in your VLIW machines so they could have a larger visible state to a patch of that graph to optimize. So in a dynamically scheduled machine, rather than a statically scheduled machine, we're actually going to have some new opportunities here, right? So if I don't have to do something that is valid for all possible executions of the program, I have to do something that is only valid for this particular execution of the program, because I'm doing all these things dynamically, I have new opportunities to move across control dependencies and find parallelism wherever it may be further afield in my program's code base or in the logical temporal execution of some number of loops, right? I don't have to actually wait for the compiler to unroll it. I can just assume I go somewhere and then find some parallelism. Yes? Any instruction. Well, only if someone can see it, right? So again, think about what we did with branch prediction, right? We can fetch a wrong path instruction in our 5-stage pipeline. Those wrong path instructions never even get to execute, let alone to write back. So if you think about what is the last place in the machine, right, that you could go and still not have altered the visible state. Well, if I haven't actually written the register back, even if I've computed it, even if other instructions have read that value that I've computed, if none of that has been written back to the register file, it hasn't really happened yet. It's fine, right? I wrote a bunch of stuff into memory. Well, if I buffer it and don't actually store it into the cache yet, that's still fine. All right, so this is all about making these things not visible until we know for certain, right, that they're actually valid. Not exactly, and we'll see the mechanisms we use. I think this is more a question of how to think about prediction more broadly as we're expanding the set of things we're predicting across, right? So the rule remains, right, that we cannot let the outside world understand that things didn't happen one instruction to its completion at a time. Nothing new. Our contract has not changed with all the hardware that we've been talking about, right? But as long as no one can see it, meltdown, Spectre, as long as no one can see it, it's all fine, right? Now, if you want to, again, get anywhere near those numbers I just showed you of 18, 150, these really, really high levels of parallelism that are, at least according to graph analysis, out there, you're not going to have to speculate past one branch. You're going to have to speculate past actually a lot of branches. You have to look at a lot of code. So we're going to go and revisit branch prediction a bit. We'll talk about that more next week. We'll assign some reading, get a better sense of what people were worried about. And so keep that in the back of your mind as to how many branches we're going to have to predict to actually get the parallelism that we want to get. Okay. Now, there is a phrase that may not yet be burned into your brain. Okay. So, precise interrupts, precise exceptions. Many people have heard that phrase before. So, the precise exception requirement is what software expects. Right, so again, if I have a program and I really was executing it exactly one instruction at a time to completion before the next instruction, then anything that went wrong during that instruction, right, has a well-defined place in the sequence of execution that things went wrong, right? So whether this is a page fault, that went wrong, but not in the way that should end your program. It's the way it went wrong in the way that the operating system should go and fix it, right? Or whether that's something that's actually going to crash the program, like divide by 0 on an integer path that's not supporting that, et cetera. Precise exceptions means that there's exactly a single instruction and a single linearization of the execution of all of the instructions that we can tie that back to. And a lot of other pieces of contract, i.e. abstractions between different pieces of software like the operating system, et cetera, your debugger, all assume that this has to be there, right? So no matter how deep and aggressive we go with our dynamic scheduling, we are going to need to preserve this if we want anyone with existing expectations about their software to use that hardware, right? So similarly, right, if anything that goes wrong with load that would crash the program can't be visible, yada yada. Okay. Nothing new there. So given all these constraints, right? It's a bit of a foregone conclusion given that we're going to spend a couple of weeks talking about it. Can implementable hardware do all the things that dynamic scheduling needs to do and actually get some of the gains that we have shown are out there? Right? Can we actually preserve that external contract while wandering around through execution to find parallelism that is latent in the original program graph that we are discovering dynamically at runtime? Right? So obviously, because we're going to talk about it for 2 weeks, the answer is yes. Right? But there are going to be some details. Right? This is, and we're going to try to not go too fast through this. And I want you to stop me whenever you have questions, because this really is different than what we've done before. Right? Okay. So let's start by hopping into the Wayback Machine. The idea of looking for parallelism that wasn't in exactly the order your instructions showed up is not new, right? So scoreboarding basically had a window of active instructions that were in the machine. They were being pulled in order. If they happened to be completely parallel, right? So no WA, no WAR, they're really just straight up actually independent, right? Then we'll execute them. Size exceptions, not so much, but it was 1964 and backwards compatibility was also not so much. So they didn't really worry about breaking their software base because there wasn't any. It was all being written new for the CDC 6600, right? In fact, the first ISA with any idea that it would be used across multiple machines is for this guy right here. Not this particular model, but the IBM 360, i.e. the fact that there even were multiple microarchitectures was novel in 1967, right? So Tomasulo at IBM came up with Tomasulo's algorithm, right? Which we won't be going over in detail as such, but we will be seeing a lot of its pieces in what eventually gets implemented. So he uses an idea of reservation stations. So each functional unit has a queue of resources that you can schedule instructions against. And this is where register renaming was first implemented in hardware. So good news, we got rid of write after write, we got rid of write after read with this register renaming. We got some distributed execution across our different functional units, and it completed things out of order. So it did not support process exceptions. Again, no deep software stack there. But this was not the model that people eventually really wanted from a software perspective. Okay. So it didn't do branch speculation because, well, it couldn't recover from it. It didn't really have precise interrupts, so you had to write an operating system that would still work even if you had only a loose understanding of exactly where in the sequence of operations your page fault had occurred. Yes. No, I mean, the register file is, it's a piece of hardware, right? It's a collection of registers. Right? It's just where the register values get written to. Out of order memory completion, also generally not advised. But again, it's 1967, and IBM is building one of the very few machines. So they, whatever they say, you just got to write your software to make it work. Right? Bit of a different market, right? Not exactly a software-dominated market. And again, also, people writing software in 1967 were mostly writing it in assembly anyway. So different world. Okay. But one of the things that I want you to, again, sort of keep track of in the back of your head, a lot of the things that we see in microprocessors started off somewhere else. They start off in mainframes. They start off in these, big, high-end computers. And the history of a lot of the optimizations we see in microprocessors have a lot to do with when did our budget on a single chip become large enough to consider doing things that had already been demonstrated as possible in a different implementation model, right? When was it going to make sense to try to do some of these things on a single chip? So if you're looking at how do you sort of map this, fast forward, better part of 30 years to a world where software is a lot more important, where we have different questions on compatibility, where we actually want the hardware changes to be transparent, right? And now we've got a lot more transistors, right? What way would we implement this known possibility to exploit dynamic scheduling using the resources that we would have on a single chip? So HPS, which is just the happens to be the initials of the authors of that paper, Wenmei Hu, Yale Pat, and I can't remember Shabanao's first name. So they said, okay, well, what we're going to do is we'll use basically a checkpoint and recovering mechanism. So most of the time, right, our interrupts don't happen. Right, the common case is you do not have an interrupt. Right. Frequently, and we'll read more on this, right? We'll go back and look at their two-level branch prediction mechanisms that some of these same people were working on at the time. Most of the time, your branch predictor is right. So if we snapshot execution, buffer some of the memory updates, and then check if anything went wrong, and if it did, flush it all, restore the checkpoint, and re-execute. Right? Then we'll be able to preserve this contract. And then what we're going to be looking at really bears a lot of its origins in something called the RUU, which was proposed by Guri Sohi in 1987. So we're going to not go exactly with the RUU model. We're going to break it up into some smaller pieces. Again, if you start looking at the diagrams of the architectures on some tech site, there are a lot more pieces today than even will be in these slides. But the idea here is you're going to have some unit that is going to be responsible for renaming your registers, monitoring the result bus to resolve the dependencies, and determine when instructions are ready to issue. Right? So now we have a very sort of different role for our hazard detector. Our hazard detector is no longer going to be sort of just looking down the pipeline and checking everything all the time. We're really moving from a polling to effectively an interrupt model. Right? We're going to set things up so that it will be notified when something is done, check what that releases, and release the things that can now go. Right? And in particular, this is going to have its roots in something called the data flow execution model. Right? So it's a different model. So in the heart of all of our out-of-order machines really is data flow. And so recall way back in week 1, reminding ourselves of the von Neumann execution model where you are exactly here, right? That determines what instruction is going to go. It goes, it advances where here is, rinse, repeat. In the data flow model, all your instructions are. And then the inputs are generated from the outputs of other instructions. When all of your inputs have arrived, you go. Now, obviously, ordering in that model is rather more complex. Right? So a lot of what the complexity here, a lot of this contract that we're obfuscation that we're doing, we have a very von Neumann contract with the outside world, but internally for performance, we want to be living in a data flow execution model as often and as deeply as possible, right? Because that's where the parallelism fundamentally is. That is where the natural execution of that graph lives. Asterisk, asterisk, memory ordering. Get back to that in a little bit. Data flow and memory ordering has some challenges. Okay, so the way that the RUU is going to support precise interrupts is not with a checkpoint and repair model, at least per se. I mean, yes, there's some repairing that you're going to do on branch misprediction, but it's going to do with a whole lot of buffering, right? So rather than basically speculate that everything is going to be fine and then restore to a checkpoint when it isn't. We're going to say, no, actually, we're just going to wait. So an instruction having done its work doesn't mean that we are done with the instruction. Right? So everything is going to be fetched in original program order. Everything is going to commit in program order. And we're going to keep all of the scheduling fun that we did in the middle, isolated from these two ends. Okay? And we'll come back to this at the very end of this deck. The RUU model is actually the basis of the tool that you'll be using to do some design space exploration, simple scalar, which came out of the same group. Okay, and again, this wasn't because no one had ever come up with out of order execution before, as we saw, right? That was, back in 1967, so 20 years previously, long since known. But no one had really come up with what was necessarily the right way to do it on chip. A debate. So let's go over, not but let's go over the flow that we will be considering in this class, right? Because you saw already, there's some alternatives. We're going with something that looks more like the second one. So fetch is still going to be pretty much just what it always was. Right? I'm going to fetch things in program order. Right? I wouldn't know how to enforce the contract that I wanted to keep, right, if I didn't know what the original order was in the first place. Right now, this is either going to be, amusingly, if you look at that particular publication from 1987, it's an out-of-order machine, but it's not a superscalar out-of-order machine. It's a scalar out-of-order machine. So life gives you some strangely optimized designs sometimes. But we are going to be thinking about a superscalar out-of-order machine where you're fetching multiple instructions per cycle. So far, nothing new. Now, decode we know. What the heck are rename and dispatch? You've got new pipeline stages. Yes. Mm-hmm. I mean, you can look at issues with overfetch where you're fetching past control decisions, but that's nothing new with respect to our in-order designs. Right? Our superscalar in-order designs already did this. So I can fetch your entire program in parallel, and that's not a problem until I try to execute it in parallel. Yeah, so this is a straightforward von Neumann program counter, still there. Hasn't gone away because our contract hasn't changed. Our ISA still happily believes, right, it's living in a von Neumann world, right? I don't know if any of you ever saw there was a movie about an East German grandma, fictional East German grandmother who'd been in a coma during the fall of the Berlin Wall. And her family tries to pretend that East Germany is still exactly as it was, so that she doesn't get shock and die, and a comedy ensues, right? So this is basically the level of delusion we're in here. We're still in a very, very von Neumann world. Everyone keeps telling grandma, yes, we're still exactly in the world you knew before you woke up, right? Everything is just as it was, right? Nothing new yet until we hit decode and rename. Okay. Decode, again, nothing new here. If you have a reasonable ISA, right, so have some sort of RISC style ISA, then you don't really have challenges in decoding instructions in parallel because decode has no dependencies among instructions to understand them. x86, it's a little more complicated, but there you go. Now, when you decode the instructions, we're going to now sort of start to have a differentiation. There's going to be a virtualization that is going to occur, right? So in your in-order machines, you talk about a register, right? We might name it T0, but let's, I think that's register, what, 8? Right? So it is the 8th entry in the register file. When you say that 32 registers, there are actually 32 registers. We're going to change the terms of that a little bit, right? We're going to say you have a physical register file that has maybe 256 registers. you have more registers, right? And then we're going to still talk about the names that are there from the ISA perspective, the architected registers, right? So this basically says when you say register 8 or T0, right, whatever, and the ISA level, these are the only ones that you talk about existing, right? But there are going to be more resources under the hood, right? If I want to have lots and lots and lots of instructions in flight, I need somewhere to put all that data, right? There are going to be a much larger physical register file. Okay, it's going to be necessary for renaming. And what we're going to do is we are going to get a virtualization where there is going to be some physical register file entry that is backing this architectural register file request that was seen in decode. So what do I mean by that? What I mean is that if I want to know at the time that I am looking for T0, I will know which physical register file has the most up-to-date version of T0. So there's going to be a table that will allow us to indirect and keep track of, okay, but which of these actually stores the version I'm referring to now? Okay, so there'll be some indirection, new hardware there. Okay. Again, we'll go into detail on all of these. Give me the overview first. We'll come back and dive deeper. Okay. But think of this as a form of virtualization. Okay, now dispatch, so renaming, well, that renaming is doing that virtualization, so it kind of does what it says on the tin. Dispatch is perhaps a little less intuitive. So the job of dispatch is to move things from the in-order front end of the machine into the data flow execution engine of the machine, right? So dispatch allocates space in all of the out-of-order structures, and does so in a way that encodes and maintains the program order from the in-order side so that it can persist across the out-of-order side and be recovered at the end when we come back to commit. Now, it turns out to not be too terribly hard to maintain in order by having a big FIFO, right? First in, first out, that'll be in order, great. It's not just a FIFO because you actually need to be able to arbitrarily update random things in the middle of it. But in terms of when they enter, when they leave, that is FIFO. That is how the order is going to be maintained. In the RUU model, there's just one RUU. You shove it into the RUU, ordered. We're going to be looking at decomposing this a little bit. This is a better reflection of how modern machines actually do work. Is it the way that modern machines exactly work? No. Again, we're still, we've moved from spherical cows, homogeneously filled with milk in a frictionless vacuum to spherical cows homogeneously filled with milk in a frictionless, not a vacuum, but still lots of abstracting going on here. Okay, so we're going to see these terms a lot: the IQ, the issue queue, and the reorder buffer. Right. Again, if you remember what the words stand for, they'll help you remember what they're for. The issue queue, right? The instruction queue is for actually issuing instructions, and the reorder buffer has to do with ordering. Okay, again, we'll see that more in a second. Okay, in order to make our lives both more and less complicated, we're also going to start doing a little bit of virtualization of how we express what needs to be done to our ISA. So you really want to think about a load or a store as a pair of necessary tasks. One is to compute the address that you are going to access memory with, and the other is to actually access memory. And we're going to split those apart, right? So from the perspective of our scheduling mechanisms, for a number of reasons, not the least of which, as you sort of physically distribute all these resources, your adder and your memory unit are actually going to become decoupled. But you're going to basically treat this as an effective address calculation. That's just an add, which is an add immediate, basically, right? And the actual load or store operation. I will show you when we look at how you would represent this, on paper for schedules. I'll show you both the decomposed and non-decomposed version of this. But in practice, always assume that they've basically been broken apart. Okay. We're going to have, again, an entirely new piece of hardware, the load store queue, right? Because again, register renaming is going to fix lots and lots of our problems with our dependencies in between registers, because those are known as soon as I decode and rename. I know exactly what resources you are asking for, what resources you will define in register space. In memory, all I know is that you read or wrote to memory. I don't know where. So we're going to need some additional hardware to resolve dependencies that are still arising, right, that need to be checked for dynamically as we execute, because we aren't able to understand whether or not they will actually represent a hazard or not. So new hardware. Load store queue. Okay. So issue is the first of our stages that is going to be done out of order. Right. Again, I don't really like. So we use the terms interchangeably, out of order and dynamically scheduled. I don't know, for some reason, every time I think of out of order, I think of it as a sign on a bathroom stall, right? Maybe it's just me. Yes, it is out of the original linearization of the program order, but you know, dynamically scheduled. So whichever one, you know, makes you feel comfortable, just run with that one in your head. So this is a data flow firing rule. So the while the reorder buffer is a FIFO, the traditional sort of queue in that sense, the queue in IQ is not really ordered, right? This is a set of instructions that have been placed into an associative data flow firing rule structure from which they can be released. Right? So anything that's in the IQ, whenever it was put in there, if it's ready to go, right, and you have the functional units downstream that could actually execute it, it is eligible to be sent down the pipe. Right? So if there are no structural hazards, data is ready to go, boom, you're going to issue it. Okay. Now, here we get a little bit of name abuse. So write back is not the same as the write back in your in-order pipeline. Very similar, but not the same, right? Because we are not writing back to the actual final program state. We are writing back internal to our data flow engine, to our out-of-order data flow engine, right? So this is not the actual update to state. This is the transmission of completed values to subsequent consumers. So those are two different things in a dynamically scheduled processor. In a in-order processor, they're the same thing, right? In an in-order processor, I complete a value, I write it back, I'm done. Right? Here, I complete a value, I'm not done. Right? It needs to be available to be consumed, otherwise, well, I can't exploit parallelism because there are dependencies still. Right? But we're going to have a notion between completing the instruction and actually committing the instruction. Again, this instruction might have done its adding of two values. It might not even be on the right path. It might not be an instruction we were ever actually supposed to execute. We don't actually know that yet because it could have been executed well in advance of the branch that controls it being resolved. Right? Dynamic scheduling is fun. Now, importantly, stores do not, cannot, must not, right, transmit their value to the cache at this stage. Right? We cannot update visible state. Write back is only updating internal state. So a store can go into the store buffer, right, when it's ready. A physical register file will get updated, right? But the architectural register file, the valid version, cannot yet. Okay. Now we're going to go back, and again, oops, let me just make this clear. This sequence here from 3 to 4, we're only showing you 2 stages. This could be an end stage pipeline in and of itself, basically, to actually do the execution, right? So when I issue something, I issue to a multiplier. It's going to take 3 cycles, 4 cycles, right? So there are actually still pipeline stages that are here, but we're we're mostly not going to be super concerned about the particulars because those are going to be per functional unit independent of each other, right? The ordering issues are taken care of here, right? If you have 3 different multipliers, I don't care what order they go in, they're independently pipelined, they just take a while before they get to write back. But don't assume that this is just a 2-stage pipeline, right? This is a piece of hardware that sends things to functional units that are themselves potentially n stages deep. Okay, now we're going to get back to order, right? So great, we did a bunch of work. We haven't told anyone yet that we've done the work, because that could be bad if it turned out we did work we weren't supposed to do, right? So what we're going to do here is we have the reorder buffer. The reorder buffer has a FIFO property, right? And we are going to look at the oldest completed instruction in the ROB. So ROB is going to have to track, have we actually done the work associated with this instruction yet, right? Now think about the oldest instruction in that ROB. Clearly, right, it must be on the right path. If it wasn't, then some branch in front of it would have been older, have been resolved at that time, and would have flushed it. So we look at the oldest instruction in the ROB. It is necessarily something we actually were supposed to have done. We can then say, did we actually do you yet? If so, great, right? Then, and only then, right, can we update the globally visible state of the machine, right? And again, we have some width that we're going to do this for. You can think of this as a sort of priority encoder, sequentially in order, up to the width of the commit of the machine, right? Oldest completed valid instructions, process them. Okay. Now, if something did go wrong, this is actually the point at which we're going to deal with it. Right? We are going to delay handling any exceptions until we know that the exception actually occurred. Right? So the completion of the instruction is going to be marked with yeah, but. Right? Because again, for the same reasoning, since we know this one actually happened, and we don't know until it gets to this point that it actually happened, we don't want to go tell the operating system that there was a page fault, right, on some instructions on the wrong side of a branch. We're going to wait till it's actually the oldest thing in the system and say, oh, and actually this is a page fault and everything after this is garbage. We're going to have to fix it and throw away a bunch of work, but at least we still have precise exceptions, right? Depending on how simple or complicated you want your branch cleanup to be, right? Again, you will have figured out that your branch went wrong before this point, right? You'll figure that out when you execute the branch, but it is sufficient, if not necessary, to also delay branch misprediction cleanup to this point in the system as well. You could be more aggressive and start doing it earlier. The challenge with doing it earlier is that if your n branches deep, figuring out what is or isn't useful to have done is still speculative. Okay. Now again, no matter how wide commit is, I can't skip over incompleted instructions, right? So if I've got a 4-wide commit, right? Let's say it's just a sequence of adds, so nothing fancy, nothing's going to cause any exceptions, and I've got my completed bit. Next one's incompleted. Next 2 are completed. Right? This is oldest, younger. Right? If this is the set of completions in my 4-wide machine, in that cycle, I am committing 1. Right? Because I commit in order. This one's not ready to go, so we stop here. So be it. Right? Doesn't matter how many of these are ready to go. We're all waiting on this guy. Okay, so here is how we would draw them. Again, not quite as many additional bells and whistles as the one I showed you a few slides back. We'll get there. But this is a nice simplified version of how you might imagine an out of order pipeline to work, right? So fetch, decode, rename, dispatch. This is an in-order pipeline, right? There might be decoupling queues, et cetera. It doesn't matter. This is an in-order pipeline. So I'm going to fetch them in order, decode them in order. Renaming definitely has to be done in order, or else I can't make heads or tails of any of the resource dependencies in my machine, right? Very order dependent. Dispatch's job, right, is to push all of the data from here over to this red portion. Red, orange, salmon. Let's go with salmon, right? The IQ, the ROB, the LSQ. Not drawing all those separately yet, right? And then when they are ready to leave the instruction queue, ending up being a stage called issue that is basically going to be the logic that understands how and when things can leave. It's then going to send them to actually get their current versions of their operands, right? Actually find those register values somewhere, do the work, tell everyone you did the work, update the buffered version of where your output is supposed to go, and the actual physical register file itself, right? And rinse repeat as things are cycling through here. Meanwhile, this is consistently looking at the tail of this, or well, head of this queue, right? Seeing, are you done yet? Are you done yet? Are you done yet? If so, update the architecturally visible pieces of state. Okay. So these are new. This portion is entirely different, right? Again, data flow-based execution. Now, even in the sort of smaller computer space, this isn't the first time people have played with data flow. But really, in particular, in the 1980s, there was a lot of interest in building data flow machines with data flow ISAs. So abandoning, the whole von Neumann architecture. Von Neumann architecture entirely, and doing data flow all the way down. Now, those machines had a fundamental challenge, right? So as I said, register ordering, we got that. How are you going to handle memory ordering? How are you going to even reason about that? So the answer that the data flow people said was, we're not going to have to, because we're going to require you to write everything in functional programming languages with no side effects. So every memory location is written at most once. No memory ordering issues. A memory has or has not been written yet, so it's got its own ready bit. We're done. As you are all not using data flow machines all the way down, clearly this did not quite go as planned, right? Has a lot of interesting properties, but good for historical reading. Now, we're still going to have to deal with some of these memory ordering issues here, but we're going to deal with it in our original ordering framework. And in particular, if you look at some works that came out of the early 2000s, where they sort of tried to figure out, are there hybrid modes? There are some fun designs that came out of there, doing like epoch level ordering rather than instruction level ordering, but still you can't buy those. They were not commercially successful. This is the model that we're all living in. Always interesting to think about the other worlds that might have been. Right? We're not living in our VLIW world. The compiler didn't solve all of our problems. We're not living in a pure data flow world where everyone writes nothing but pure Haskell. Yeah, and it wasn't Haskell. Haskell came later, but same idea. We're living in a world where people write buggy C programs and want the hardware to run that buggy C program as fast as humanly possible. There we go. Okay, all right. So again, here's another way to sort of view this sequencing, right? And we have original program order. Now again, how are we going to keep fetching instructions if all of the actual execution of which way we're supposed to go is happening in this middle here, right? Well, there's going to have to be some sort of feedback to guide that front end, right? So there's going to be a lot of branch prediction, right? These machines are going to be sensitive to branch prediction accuracy in a way that your simple 5-stage in-order pipeline was not, right? Because you're going to make speculations on top of speculations on top of speculations on top of speculations on top of speculations, like it's 2006 and you're investing in the housing market, right? So we're going to keep our program over here. This part's easy, FIFOs. But this part here, speculative control is going to be a little bit interesting. Okay. So again, keep that in the back of your mind. Mapping and wrestling. Okay, so let's walk through this with a code example. Right, so here's a dynamic trace of instructions. So there are only up to here, these are the actual instructions. These are subsequent executions of the same loop. Right, so we're only talking about 1, 2, 3, 4, 5, 6 static instructions, but it's a loop, so it executes many, many, many times. Okay, we have not unrolled this. Right, the compiler didn't unroll this for us. Compiler just gave us a loop. But if you look at this execution over time, right, so this is a time window, not a code address window. Right, they're strongly correlated, but different axes. Let's take a look at how this might play out. Okay, so load, add that's dependent, store dependent on that, and subtract. I want to reuse this. Let's assume that there's a cache miss for 3 cycles because we're hilarious optimists living in an a chronological world with schizophrenic technology levels. Let's assume for the sake of argument, so that fits on the slides, a 3-cycle stall. Right, so there are going to be some dynamic variable behaviors that we weren't able to expect. Right, they're going to be the wild hazards that were always there. There's going to be branch prediction. So let's assume that it is predicted correctly taken. And let's assume that from here on out that we don't have some more cache misses. Let's start to think about how this would flow down our out-of-order pipeline, right, and understand what's going on here. Okay, so all of our read after writes, right, and there are plenty, need to be obeyed, right? If I define something and then I read it, I need to get the value that it should have at the time in this order based on the original contract. These write after reads, plenty. These write after writes, we are going to get rid of these with hardware renaming. We're going to show you how the hardware gets rid of these. Because again, across loop carried iterations, right, the hardware doesn't really see loops. Hardware sees a sequence of instructions that you're fetching. So dynamically, these are the scheduling constraints. So here's this nice, lovely graph, and the hardware needs to, quote unquote, understand it, or at least understand how to obey it, right? As we all know, the machines don't really understand anything. Certainly, anyone who's been chatting with ChatGPT knows that it understands nothing, and anyone who has been chatting with Bing's ChatGPT-based search client understands that, wow, that program needs some therapy. I don't know if you've read some of the most recent articles. They're fascinating. Okay, lots of true and false dependencies. Right, there is some inherent parallelism here, but we're gonna have to look around to go and find it. Okay, so how is hardware going to do register renaming? Okay, so we're gonna do this via this virtualization mapping. Right, so remember, single static assignment. How does it work? Every time you write a new value, you get a new name. Then I don't have write after read, and I don't have write after write, right? Because you got a new name. So they're not asking for the same resource. So how are we going to handle that? Well, by having many more physical registers, then I will actually have architected registers. So every time you write into T0, it's going to get a new physical register name to write into. Obviously, that's still going to be finite, right? Compiler has the joy that it can allocate as many names as it wants. Hardware, it's going to be many, but it's still going to be finite. You can run out of places to put things. Right? You're going to have a finite sized window. Right? Again, if you're trying to think of you showed me a graph. That graph said 150-way parallelism. Why do I have an IPC of 3 on my actual machine? Finite boundaries matter, right? So this will be one of them. So you can run out of physical register names, okay? But there are going to be plenty of them. Okay? So a lot of this is going to be either indirection or just accounting. Okay, so the free list is probably not actually a list. Don't think too much about the word list. The free list is a stores what registers are not currently in use, and you can retrieve some available things from it. Right, a circular buffer would work just fine. Right, think of it logically as some free list. This map table is what is going to be keeping track of our virtualization. Right, because it wouldn't do us any good to say, oh, yeah, single size assignment, T0, yeah, you're gonna write into P1. Next time I see T0, you can write into P3. Oh, where's the current value of T0? I don't know. I just wrote it somewhere. Right, we're not gonna go looking up, right? So no, we're gonna have to keep track of where everything is, right? And because again, we don't just write into registers, we also read from them. Right, so if I write that the current version of T0 is in P3, and then in the next instruction, I read from T0, I better make sure that what I read from is P3. Right, so we are going to rename all of our original instructions in terms of entirely a set of both writing and reading physical registers. Yes? No memory here at this point. These are just registers. Yeah. So you can have two different designs. So you could basically say that I don't actually have an actual architected register file. I just have a current valid mapping. Right? I can just have a bit that says this is and should be treated as the legitimate, rightful T0. Or I could actually have a separated actual, fixed size architected register file that is both physically and logically separate. Depending on the number of architectural registers you have, depending on, there are a few different styles of implementing out of order. They have some different trade-offs in terms of power and communication efficiency. One or the other may make more sense. From the perspective that we're going to be talking about, let's assume without loss of generality that they are actually two separate sets of resources. It doesn't really matter. As long as they're logically separable, we're in good shape. Yeah. But that is a design choice. Okay, so let's do some renaming. So here's our code. We're not going to walk through all of the iterations. We're going to assume that register 0 is in P0 always and forever, since register P0 is always, it's always 0 and never gets written. So just keep that in the back of your mind, that somewhere there is a 0 register still. Could you do it in other ways? Yes. This is actually how you want to waste one of your free slots with this? Probably not. We're just going to assume P0 is always 0. Makes our generalization of the rules simpler. Fewer special cases, easier for pedagogy. Okay, so that out of the way. Let's start thinking about what we need to record. So let's say that this is the first instruction that's coming into rename. Again, rename is done in order. So whether rename is 1 wide or 5 wide, unless I actually have to track where I ran out of resources, it won't matter. Right? The final mapping I produce would be the same. Just a question of when. Right? So I'm going to say, okay, here is my current mapping table. Tells me S1 is in P1, S2 is in P2, T0 is in P3. And 4, 5, 6, 7, and 8 are available. Nothing is currently mapped to those. They're not in use. These are my initial state, 2 new structures, in comes the instruction. We're going to rename it thusly. See if we can track why. We're going to look up where S1 is. Anything I am reading, I'm going to look up its current mapping. It says, I need to read S1. Where is S1? S1's in P1. I'm going to read from P1. Okay. I am going to write something. So to write something, I don't care where T0 is. I care where there is an available resource to write something new. and take that off the head of the free list, thusly. I do, however, have to remember, I need to update this value here as well, but I do actually want to remember where T0 used to be. All right, so I am going to keep track of what register I overwrote. Right? This is the structure we have. Okay, so this is another field. This is the instruction itself renamed. This is a piece of data that is going to flow with that instruction all the way through the pipe. Right? This is what I'm reading. This is what I'm writing. This is the old value of what I'm writing to. Okay. So let's launch a Kahoot. That will be about where today ends. Okay, survey says I need some chalk. Okay. 423001.